An offline verifiable credential has one permanent weakness: the issuer can sign it once, but reality can change later. A driver's license can be suspended. A student ID can be revoked. An employee badge can lose access after termination. If every verifier has to phone the issuer about one specific credential, privacy collapses because the issuer learns where that credential was shown. Credential status lists solve that problem with a shared artifact instead of a per-credential API call. In the W3C model, the credential carries a credential status entry that names a status purpose, a list URL, and an index into that list. The verifier fetches a signed Bitstring status list credential, expands a compressed bitstring, and inspects one position. 0 means the status is not asserted. 1 means the status is asserted, usually revoked or suspended depending on the purpose. 1 URL, 1 index, 1 bit. That is how you let a credential work offline most of the time while still giving issuers a privacy-preserving way to change its status later. Identity Expert, powering you to be an expert in identity. In this guide, why offline credentials need a shared status channel, how Bitstring status list entries map one credential to one bit, which privacy traps matter most, and why revocation differs from suspension. Think about a large office building with 100,000 employee badges in circulation. Security at the front desk needs to know whether a badge is still valid, but they do not want to phone HR every time someone walks in. A direct phone call would tell HR exactly which employee showed up at which building and at what time. It would also become a scaling disaster during the morning rush. The office solves this with a shared status board. Every badge has a row number. The security desk checks the board, looks at the one slot for that badge, and sees whether the status is active, suspended, or revoked. HR updates the board when someone's employment changes, but HR does not get a real-time alert every time the badge is presented. Credential status lists work the same way. The verifier does not ask about your specific credential. It dereferences one shared list, checks one index, and learns whether the status tied to that credential has been asserted. Status checking has to solve 4 problems at once. First, privacy. An issuer should not learn every verifier interaction just because a credential needs revocation support. Second, scale. A status mechanism has to work for very large populations of credentials without creating a unique server lookup for every presentation. Third, semantics. Revocation and suspension are not the same thing. Revocation is typically final. Suspension is usually temporary. A verifier needs to know which meaning it is evaluating. Fourth, freshness. Offline credentials are powerful precisely because the issuer is not in the loop, but that means verifiers need a clear, machine-readable way to fetch up-to-date status when policy requires it. The W3C answer is the credential status hook in the verifiable credentials data model plus a Bitstring status list entry type. The hook gives the verifier the status purpose, the status list credential URL, and the status list index. The Bitstring status list specification defines how to encode the shared list, how to verify it, and how to read the right bit without asking the issuer about one credential at a time. The runtime flow is simple. Step 1. The verifier receives a credential or presentation containing a credential status object. That object says which status purpose is being checked, where the status list credential lives, and which index belongs to this credential. Step 2. The verifier dereferences the status list credential URL and verifies the proof on the returned verifiable credential before trusting anything inside it. Step 3. The verifier confirms that the list actually covers the same purpose, such as revocation or suspension. Step 4. It reads the encoded list value, multibase decodes it, gzip, expands it into a raw bitstring, and inspects the position identified by status list index. With the default status size of 1, the answer is binary. A 0-bit means the status is not asserted. A 1-bit means the purpose is asserted. If the purpose is revocation, the credential is revoked. If the purpose is suspension, the credential is currently suspended. The important design detail is that the verifier checks a shared signed artifact, not a per-credential query endpoint. On the wire, there are really 2 payloads to remember. The first is the credential or the verifiable presentation carrying it. That payload includes credential status with 4 fields that matter most in practice: type, status purpose, status list index, and status list credential. The second payload is the status list credential itself. When the verifier dereferences that URL, it receives another verifiable credential whose credential subject contains a Bitstring status list object and an encoded list field. The verifier verifies the proof on that status list credential, confirms the status purpose matches the entry on the original credential, expands the bitstring, and reads the correct position. The verifier is not asking, is credential number 94567 revoked right now? It is asking for one shared signed list that already contains the answer for many credentials at once. That distinction is what preserves privacy and keeps the mechanism efficient. 3 threat classes matter most here. Threat 1 is per-credential tracking. A malicious issuer can destroy privacy by publishing a unique status list for every credential or by assigning obviously correlatable indexes. The mitigation is large shared lists, random index allocation, and avoiding one-to-one mappings between a credential and a list. Threat 2 is stale status. If a verifier caches the list too long or ignores validity policy, a recently revoked credential may continue to pass. The mitigation is explicit freshness policy, verifier caching with disciplined revalidation, and CDN distribution that hides verifier access patterns without freezing the list forever. Threat 3 is incorrect processing. If an implementation skips proof verification, checks the wrong status purpose, or misreads the bit ordering, it can invert the answer and accept a credential that should fail. The mitigation is to follow the W3C validation algorithm exactly. Verify the list credential, match the purpose, decode the bitstring correctly, and read the index the same way every implementation does. The status story is still evolving, but the broad direction is clear. Verifiable Credentials Data Model v20 made credential status the generic hook for expressing status information. Bitstring Status List v10 then turned the popular status list pattern into a W3C recommendation in May 2025. Standardizing the shared bitstring approach that many wallet ecosystems were already converging on. The newer specification is broader than the older Status List 2021 pattern because it cleanly models both revocation and suspension, allows multiple status entries on a single credential, and can represent richer multi-bit status messages when ecosystems need them. At the same time, the hard problems have shifted away from data structure design and toward operational policy. How fresh must a cached list be? How often should an issuer rotate or republish it? When does a verifier fail closed if the list cannot be reached? Those are ecosystem choices, not unanswered model questions. The durable takeaway is that status for offline credentials is no longer an ad hoc extension. It is now a standardized part of the W3C Verifiable Credential Toolbox. All primary sources cited in today's guide are listed on screen. The description below links directly to the W3C sections that define credential status, Bitstring status list entries, the validation algorithm, and the privacy guidance behind shared lists. If this helped you understand revocation and suspension in verifiable credentials, subscribe to Identity Expert for more standards deep dives. Thanks for watching. If there is a wallet standard, credential format, or protocol profile you want covered next, leave it in the comments. Subscribe and hit the bell so you never miss an Identity Expert deep dive.